RLC circuits. Resistor, inductor, capacitor. So I want to model all this stuff. Some of it we can solve analytically, and we'll do that. Starting with the always awesome Phet simulator. Let's just do this. So here I have a capacitor, I have an inductor, I have a battery. I'm going to charge the capacitor. It's hooked up to the inductor. Doesn't really matter. And right there. Oh, how do I do that? Close the switch. Let's plot this voltage across the capacitor. Okay, so now it's just constant right there. It's not anything interesting. But now what happens when I open this switch? Oops, I burnt my thing. So you see that we get this, I'm going to zoom out, this oscillating voltage, which is kind of cool. There's no resistance, so this will keep going forever. Animation speed slowed. Okay, that's fine. So let's set this up. A charged capacitor hooked up to an inductor with no resistance. And then we'll model that, and then we'll do it with the resistor in there too, an RL circuit. Once you get that, you could put a voltage source in there, an alternating source, a whole bunch of awesome stuff. I don't know how far I'll go. Let me pause this because it's getting angry. Okay, let's look at the Bane idea right here. So we have an RLC circuit, has a resistance and an I was so excited to start this. I put those backwards. A capacitor and an inductor. And we're going to start with this case right here. But in general, the voltage across a resistor is the current, whatever that may be, times the resistance. Now, the voltage is such that this side will be positive and that side will be negative if the current's going that way. The voltage across a capacitor is Q over C, where, again, it depends on which side is positive and which side is negative. The voltage across an inductor is proportional to the rate of change of current, right? Because what happens here is that you have these coils of wire. When the electric current increases or decreases, you change the magnetic flux through these other parts, which creates a curly electric field that creates a back EMF. So it always opposes the change, and that's why there's a negative sign there, but I just talking about the magnitude. So we have this IR, this Q over C, and this DI dt. And you'll notice that if you say I is dq dt, then these are all functions of charge, right? Charge, first derivative of charge, second derivative of charge. Because I can write that as L, second derivative of Q with respect to T. Okay, go over here. Let's assume that I have a capacitor with a charge, initial charge Q0 on it. And I have just an inductor hooked up to it with an inductance of L. The loop rule still holds, right? So if I start here and go around the loop, then I get Q over C minus this voltage, or plus actually, because minus and minus when going that way. If that, because once that connected, the current's going to be increasing. So it'll be plus L dq di dt equals 0. And I can write that as Q over C plus L second derivative of Q with respect to time equals 0. Now, if you haven't had differential equations, don't worry. This just says there's some function of charge Q. I take the second derivative right here and I add these together and get 0. So let's just move this to the other side and rewrite this so I can get second derivative of Q with respect to T. It's going to be negative. I'm going to divide both sides by L. 1 over LC Q. So this says, what function do I take the derivative of twice and get the same thing back, right? That's what that says. Well, we could guess a solution there. I'm going to guess. Oh, this is second derivative. Guess. Let's guess Q as a function of T is Q0 cosine omega T. Right? Because this says that if I take the derivative of cosine, I get negative sine. If I take the derivative of sine, I get cosine. So I will get, oh, this should be, yeah, that's right. So if I plug this in up here, I get negative Q0 omega squared, because I'm getting an omega squared term because I take the derivative twice, cosine omega t equals negative 1 over LC Q, which is Q0 cosine omega t. So this will be true if omega squared equals 1 over LC. And so this tells me the oscillation frequency of that particular element, right? Which we saw. It was a cosine function. Now let's model this in Python, because there's another way to solve differential equations. Suppose that I know this. I'm going to start with that. The second derivative of Q with respect to time is equal to negative 1 over LC Q. That's what I have. Suppose I break this into short time intervals, delta t equals 0.001 seconds. During that time interval, the charge will change, and so dq dt will change. But it's possible that I could assume that this value is constant. If that's the case, I can assume this is a constant. And I'm going to write this second derivative as q double dot, just to make things look a little bit easier. And then I can say that's equal to the derivative of dq dot dt, where q dot is the first derivative. And I can write this as q2 dot minus q1 dot over delta t. So Q2 is the current, right? That's the first derivative of charge is the current at the end of the time interval, and that's at the beginning of the time interval. If I solve this for Q2, I get Q2 dot. Q2 dot is Q1 dot plus Q double dot delta t. And so I can calculate Q double dot from this. I can put it in here and calculate Q2 dot, the current at the end of the time interval. So this assumed that the charge didn't change, which it did. Okay. Now I can do the same thing. I can assume Q dot is constant, and I'm going to write that as delta Q over delta T, or Q2 minus Q1 over delta T, and I get Q2 equals Q1 plus Q dot delta T. Now, what I've done is I've started this time interval. If I know the initial charge and the initial current, I can find the charge and the current at the end of the time interval. If I know delta Q double dot, which I can do from up here. So this is called an Euler calculation, and the numerical method, an Euler method. And the idea is calculate the second derivative from this equation. Use that value to update the first derivative. Use the first derivative to update the second derivative. Now, there is one small problem here. And that problem is that Q is the charge on the capacitor. And Q dot is the rate of current. So Q dot is going to be negative dq dt. Okay. But we can break this up into 1,000 time intervals to get 1 second of data, and then we can plot that. We can plot Q as a function of time, and we can compare that to this. Q as a function of time, Q0 cosine omega t. So we're going to do it two ways. We're going to do this. We're going to plot that. I do need values for omega is 1 over the square root of LC. So I'll get those from the simulator, so it'll be the same. Let's jump to Python and let's do this. Okay, so here we are. The first thing I want to do is to get my values for my capacitance and inductor. So if I click on this, I have a capacitance of 0.1 farads and an inductance of 5 henries. Okay, so let's go over here. I'm in Python. I will give you the code. I'm going to make a graph. G1 equals graph, X title equals time, Y title equals VC, the voltage across the capacitor. And then let's put width 400, height 200, and I'm gonna make two graphs. So F1 is gonna be my analytical curve, G curve, color equals color dot blue, and then my other one, F2, is G curve, color equals color dot red. So now let me put my values in there. Oh, I do need a value of Q0, right? Q0, if I go back to the simulator, I have a 9-volt battery. So I can calculate Q0. So VB equals 9, and that's going to be Q over C. So C is 0.1, L is 5. Q, I'm not even going to say Q0. Q is going to be, let's see, V is Q over C. So V times C. Right. VB times C. That's right? V is, yeah, okay. I also need my initial derivative, right? I need to know the current at the beginning. So Q dot, I'll call it DQ. Let's call it Q dot. Q dot is 0. I need time. I need dt. Let's run this for 1 second. Let's make this bigger. While t is less than 1, I'm going to give it a rate of 1,000. So this will take 1 second to run. Rate 1,000 just says don't do more than 1,000 calculations per second. So the first thing I'm going to do is to calculate the second derivative from the differential equation. Q double dot d dot, I'm going to call it, is negative 1 over L times C times Q. And so I have a value for Q, right? It starts off with some whatever that is. It is what it is right there. So there's a number. Now I'm going to use that Q dot to update Q, that Q double dot to update Q dot. Q dot equals Q dot plus Q double dot times dt. Now I'm going to update Q. Q equals Q plus Q dot times dt. And you'll notice here that I'm not calling it Q1, Q2, Q3 because this in Python updates those values. I don't have to worry about keeping track of all the different values. They're just going to get updated. Now I need to update time, t equals t plus dt, and now I'm going to plot it. Let's do F1. F1 dot plot t, and the voltage across that's Q over C, right? I'm plotting the voltage. So Q divided by C, and let's run that. I didn't even save it. But it worked. Check that out. Okay, we need to run it for a little bit longer time. Let's run it for 4 seconds. It's going a little bit slow, but that's fine. It should be the same as what we had in the other thing. Okay. Look how simple this code is. I have stuff right here for graphing. I have just the initial conditions, and then my loop. Calculate the second derivative, use that to update the first derivative, use that to update the charge, and then plot it. That's it. Now let's compare. Let's just calculate what it should be. So I'm going to say omega is 1 divided by the square root of L times C. And then I can calculate Q theoretical is Q0, and let's put Q0 up here. Q0 is VB times C, because that Q is going to change. I wanted this like that. Q0 times cosine omega times T. And let's plot that. F2 dot plot T Q T over C, and run it. Oh, you only get one graph. You know why you only get one graph? Because they're right on top of each other. Okay, they're identical solutions, and that's pretty cool. Okay, now let's go ahead and add in a resistor and then model that, because that's something that we can't easily calculate analytically, but we can do it numerically. So going back to Phet over here, let's break this up. Let's take this off. I'm going to add in a resistor. So I'm going to click this and cut that. And and I still want to charge the capacitor, but it gets, oh, it should be fine. If I close that switch, let's see, I don't like that. Cut that. Okay. Put a wire there. It will still discharge the capacitor. Oh, it caught on fire. Okay. It caught on fire, but then it stopped. That's fine. And then up here, let's put a resistor. So I have a resistor, an inductor, and a capacitor all in series. The capacitor is going to be initially charged, but you can see how we could easily fix this situation. I'm going to put a switch here. Ugh, terrible circuit. Okay, whatever. Okay, it's fine. It's fine. Now let's measure the voltage across the capacitor as a function of time. Let me see what my resistor is. 10 ohms. Let's change that to 1. One. Okay, here we go. You ready? Let's play. Play and close the switch. And zoom in. Okay. So you see we still get this oscillation here, but the amplitude is getting smaller and smaller as a function of time. So how can we change our code to include that? Well, we just need to add in that other term, right? We need to change our differential equation and then go back and change our Python. So let's do that. Let's change our differential equation. So now we have this. So our loop rule is going to be the voltage across the capacitor, which is Q over C, and then minus IR minus the derivative of I with respect to T equals 0. That's the loop rule, right? So I already had that. Now again, these are actually going to be equal to plus when I switch it to actual Q versions. But I'm going to write this as Q over C. Is it plus? I always get this backwards. Let me see what I put. I wrote it down. Yeah, they're going to be plus because the current is the flow of charge, but Q is the charge on the capacitor. So it's going to be plus Q dot R plus, 1 over L. No, L. Plus L Q double dot equals 0. No, that one's minus. One of them is minus. Let's wait. No, that one's minus. So leave these as minus. Minus, minus, minus. No, plus. No, they are plus. Okay. Yeah, they're plus. So then I solve for Q double dot. Q double dot is going to be equal to negative Q over LC minus Q dot over RL. So I just have to change my differential equation. It's not even too hard. Let's go back to Python and just modify that. So here we are with Python. I'm going to add in my value for R. R equals 1. So now my differential equation is going to be this minus Q dot times R over L. That's all I have to do. The rest is the same. I'm going to leave it plotting. I'm not going to, I guess I should plot that. Let's leave that theoretical plot on there. That's with no resistance. But I'm going to run it. And the blue curve is my actual data. And you'll see that it's getting smaller and smaller. And let's run it for a longer time. Let's do this at 5 times the speed, 8 seconds. And that pretty much agrees with the experimental evidence from Phet. Now, I'm going to stop here. But let me draw a picture of something that you could do. not too terribly difficult. And I'll let you do that and play around with it, because it's a complicated mathematical problem, but it's pretty easy to solve numerically. Let's look at another circuit. I'm running out of paper here. Resistor, capacitor, inductor, and what's down here? V is a function of time. So you can put an oscillating voltage source in here, an AC voltage source, and it's going to make the differential equation pretty complicated because you have another function in there. But numerically, you just calculate this value and add it to your differential equation. It's not so bad. What you can see is that you get, if you play around with the frequency of the voltage, and if it matches up some parameters over here, I'll let you play with it, you can get resonance. It's kind of cool, okay? But I'm going to leave that as a homework assignment for you. I will put the link to the code down below, so you'll have that that I made, not too complicated, and that's that. Oh, and Phet. Don't forget about Phet. Phet's awesome. The end.